previous lecture we considered the input output relations for linear time invariant systems, and we showed that if f of t is the input, x of t is the output, it is obtained as convolution between f of t and the impulse response function of the system, and that is represented through this. This is time domain input output relation. If input is specified in terms of its Fourier transform, the output Fourier transform will be given by multiplication of the frequency response function h of omega and the Fourier transform of the input. So, a convolution operation in time domain becomes multiplication in frequency domain. The definition of impulse response function itself is shown here. H of t is the response of the system to an unit impulse applied at t equal to 0, and similarly the frequency response function is the amplitude of the steady state response of the system to an harmonic excitation. This is h of omega. This f of t and f of omega form Fourier transform pair, x of t and x of omega form Fourier transform pair. Similarly, h of t and h of omega form Fourier transform pair. So, this is in the nutshell the summary of input output relations for linear time invariant systems. We also considered the problem of uncertainty propagation. If f of t is the input and if f of t is modeled as a random process, then for every realization of f of t there will be a corresponding realization of x of t that can be obtained, for instance, via a convolution between impulse response function and f of t. So, if we are given samples of f of t and the initial conditions, the problem of uncertainty propagation consists of finding corresponding samples of x of t. This would mean that we may have to solve a family of deterministic problems. Each of this problem corresponds to one realization of f of t to produce one realization of x of t. But if f of t is specified in terms of its mean, how one derives the mean of the response in terms of mean of f of t? Is it possible? If so, how to do it? Similarly, if one has description of covariance or the power spectral density function in the frequency domain, then correspondingly how to define the covariance of the output? Can we define the power spectral density for x of t? If we can define, how to find it? Similarly, such questions can also be asked with respect to higher order moments or for the probability density functions. For example, if we are given the first order probability density function of f of t, what is the first order probability density function of x of t? So, similarly you can repeat this question for nth order PDF for f of t and corresponding nth order PDF of x of t. So, the basic fact that has to be emphasized here is that the propagation of uncertainty in such systems follows laws of mechanics. That has to be understood because the output is obtained as a transformation of f of t. Therefore, essentially we are making transformations on random quantities, and as we already seen there are rules for handling such transformations of random quantities, and they come into play while solving this problem. Now, we will reconsider the problem of a single degree of freedom system under random excitation. Let f bar of t be a random excitation and let x naught and x naught dot be the initial conditions. Let mean of f bar of t be mf of t. Now, what we will do is we will introduce f of t such that f bar of t can be written as sum of the mean component and a fluctuating component, so that this mean of this fluctuating component can be 0. Now, if we take expectations on both sides on this equation, we get m of x double dot plus c of expectation of x dot plus k into expectation of x. This must be equal to expectation of f bar of t. Similarly, the expected value of initial conditions will be x naught and x naught dot. So, in our analysis we are assuming that x naught and x naught dot are deterministic. They can also be random. For the time being we are not including that possibility. Now, this is a equation that governs the mean, and this is a deterministic equation. So, we can use the standard formulation and write the expression for time history of this mean in terms of initial condition x naught dot and this Duhamel's integral in terms of mean of f of t. So, this expected value of f of tau is mf of tau, and this is nothing but mx of t. Thus, we can consider this equation schematically as shown here. What goes into the system is the expected value of f of t, and what comes out is the convolution between h of t and mf of t to produce the expected value of x of t. Okay. So, this is the input output relation for the expected value of the response in terms of expected value of the input. Now, just as we wrote f bar of t to be f of t plus its mean, we can also write the mean the response process itself to be sum of its mean and a random fluctuating component whose mean is 0. Suppose now if I substitute this into the governing equation, I will have for x of t expected value of x double dot of t plus y double dot of t, that is what is written here. Similarly, for c x dot I will have c into expected value of x dot of t plus y dot of t. So, that is here. Similarly, for ky kx I will have k into expected value of x of t into ky, this is this, and for f bar of t I will write mf of t plus f of t. We have already seen that the sum of this 3 terms is equal to this, because that is the governing equation for expected value of x of t. Therefore, we can cancel out these 3 terms, and what we are left with is my double dot plus cy dot plus ky equal to f of t. Similarly, the initial conditions if we now consider, expected value of x of 0 plus y of 0 is x naught, but we already seen that expected value of x of 0 is x naught. This would mean expected value of y of 0 would be 0, and by the same argument expected value of y dot of 0 is also 0. So, for this random component y of t, we have now an equation where right hand side is a random process with 0 mean and the system starts from rest. So, for such systems, that is for systems starting from rest, the Duhamel's integral provides the complete solution. So, y of t can be written as 0 to t h of t minus tau f of tau d tau. Just to verify, you can take expected value of y of t, that is expected value f of tau, this is 0, therefore, this integral is 0. How about second order properties? Now, you consider expected value of y of t1 into y of t2. So, you have to multiply a Duhamel integral corresponding to y of t1 with another Duhamel integral corresponding to y of t2. So, if you do that, we get a double integral where now the integration is on tau 1 and tau 2, and this t1 and t2 appear in the integrand here, as well as in the arguments here. So, we know the expectation operator, assuming that this integration and the expectation operator can be interchanged. If we do that, we will be left with expected value of f of tau 1 into f of tau 2. This is deterministic, so this can be pulled out. So, we get now here the expected value of the response process, the covariance of the response process in terms of covariance of the input process. So, this can be viewed as the input output relation for covariance of the output in terms of covariance of the input. Now, in the expression for Ryy of t1 comma t2, if I take t1 equal to t2, I get Ry of t1 comma t2 is variance. Mind you, mean of y is 0, therefore, autocorrelation function and autocovariance function are the same. So, therefore, at t1 equal to t2, the mean square value and variance will be the same. So, that integral the right hand side here now becomes wherever there is T1 and T2 I will replace by T and I get this expression. So, one thing that we can notice immediately is if you know the autocovariance of the input, you can find the autocovariance of the output. That means to find autocovariance of the output, you need to know the autocovariance of the input. If you know only the variance of the input, you will not be able to find variance of the output. So, to find variance of the output, you need to know the covariance of the input. Okay, that has to be understood. Now, the autocorrelation function is a second order property. We can consider higher order moments. So, we can take expected value of y of t1, y of t2, y of t3. This will be a triple integral, and now expectation will be taken on f of tau 1, f of tau 2 and f of tau 3, and this integral can be rearranged in this form. So, I have in the integrand expected value of f of tau 1, f of tau 2 into f of tau 3. So, this is the third order moment of f of t. If you know the third order moment of f of t, you can derive the third order moment of the response. So, we can generalize this now and say in general for linear time invariant systems, the knowledge of nth order moment of input is adequate to determine nth order moment of the response process. This would mean the moment equations are closed for linear time invariant systems. This is not in general true for dynamical systems. For instance, if you have a nonlinear system, this is not true. This can be seen if you consider a simple nonlinear system where I have now a cubic nonlinear term. If I now consider expected value of the response, this will be expected value of x double dot plus c into expected value of x dot plus k into expected value of x plus alpha into expected value of x cube is equal to expected value of f of t. Now, you please notice here the equation for expected value of x contains the expected value of x cube. If you now try to write another equation for expected value of x cube, for instance, you can multiply this equation by x square of t, x square of tau for example, and take expectation on both sides. You will immediately see that you will need, if you do that, you will need a expected value of x cube of t into x square of tau, again which will be unknown. So, the moment equations here will never get closed. They will form an infinite hierarchy of equations which at no stage yield an acceptable set of equations which can result in a solution for the moments. So, this is known as the closure problem. Later when we discuss some issues about nonlinear random aberration problems, we will briefly touch upon this again. Now, to illustrate the idea that we just now described, we will consider now the response of a single degree of freedom system under Gaussian white noise excitation. The governing equation here is again mx double dot plus cx dot plus kx equal to f of t. We will assume that system starts from rest and expected value of f of t is 0. Without loss of generality, this assumption can now be made that mean of the applied force is 0 and initial conditions are 0. That means system starts from rest and excitation has 0 mean. If any of these conditions are violated, we can solve a separate deterministic problem and find out the contribution from non-zero mean for excitation and non-zero initial conditions. That is reasonably straightforward. So, we will focus only on issues related to randomness in f of t. So, expected value of f of t is 0. Since we are saying that f of t is a Gaussian white noise, the expected value of f of t1 into f of t2 is I into Dirac delta of T2 minus T1. Now, x of t can be written in terms of the Duhamel integral again as shown here. Now, if you consider the expected value of x of t, expected value of x of t is expected value of f of tau will come here in the Duhamel integral. This is given to be 0, therefore, this is 0. The system starts from rest, therefore, there are no other terms in your expression for x of t. How about covariance of x of t? So, you now consider expected value of x of t1 into x of t2. So, this is expected value of this double integral. Here we can get the autocovariance of the output in terms of autocovariance of the input in this form, and for RFF of tau 1 comma tau 2, now I will write the expression for autocovariance of a white noise, which is I into Dirac delta of tau 2 minus tau 1. So, one integration can easily be performed. I can replace tau 2 by tau 1 and I get h of t1 minus tau 2, h of t2 minus tau 2, and only one integral remains, that is integration with respect to tau 2. So, this is 0 to t2 and one integral with respect to tau 2. Now, we know h of t is given by this damped exponential sinusoidal with exponentially decaying multiplier. So, this is 1 by m omega d exponential minus eta omega t1 minus tau, etc. So, this can in fact be integrated using straightforward application of rules of integral calculus, and we would get this expression. This is, I have written it in a slightly form that can help us to analyze the nature of this function. So, there is a function chi of t sitting here, and this chi of t is given by this expression, and there is a multiplier which is exponential minus eta omega t2 minus t1. If we now carefully look at this expression, we can see that Rxx of t1 comma t2 is actually function of both t1 and t2, because there is a t1 plus t2 here, there is a t1 here, and there is sin omega t1 plus t2, etc. So, from this we can conclude that x of t is a non-stationary random process. It has 0 mean, constant mean, but it has a time varying autocorrelation function which is not a function of time difference. We can consider the variance by replacing t1 equal to t2 equal to t, and if we perform this integration we get this expression here. Here again you can see that variance is a function of time. Therefore, again it points towards the fact that response is non-stationary. What would happen now if, for example, in the expression for variance time becomes large? If you take a look here, the term inside this braces is sinusoidal and there is a constant here, cosine and sine terms, they are bounded between plus and minus 1 for all values of t, but this multiplier function exponential minus 2 eta omega t ensures that as time becomes very large, the product of this function and the terms inside the braces go to 0, and we are left with this one constant term. So, the variance that is here as t becomes large becomes a constant. How about autocovariance? You now take t1 to infinity, t2 to infinity, but t2 minus t1 to be tau. If you put that limit, what happens? Here as t1 goes to infinity, the multiplier to this terms inside this brace goes to 0, whereas the terms inside the second bracket have sine and cosine, and also they are functions of t2 minus tau 1. Therefore, t2 minus tau 1 is going to tau. Therefore, I get the autocovariance function to be function of only tau, okay? And therefore, we can conclude that as time becomes large, the process becomes weakly stationary. So, I have shown a few plots of autocovariance and variance. This is a plot of variance. System starts from rest and this is for different values of damping parameter. So, as you see here, as time becomes large, after some time there is initial growth and after some time the response reaches a constant value, the variance becomes constant. The steady state value, that is the steady state value of the variance, depends on damping. So, lesser the damping, higher will be the response variance, and not only that, the time taken for the system to reach steady state increases with reduction in damping, because the function exponential minus 2 eta omega t decays relatively more slowly for lesser values of eta. So, in any case, as long as eta is not equal to 0, a steady state exists and variance becomes constant. If damping is 0, the system will never reach steady state. Here I have shown plot of autocovariance function T1 comma T1 plus tau as a function of T1 and for different values of time lags. So, here again what happens, for small values of T1 the function is varying with respect to time, but for large values of T1 this function also becomes constant. So, that means for large values of T1 the autocovariance function simply becomes function of tau. This is tau equal to 1 second, this is 2 second, this is 1 second, this is 2 second, this is 4 second. So, it reaches different values. This is the plot of r of tau as a function of tau. You can see that this is shown for both positive and negative time lags. You can easily see that this function is symmetric about tau equal to 0 and it represents a decaying sinusoidal function. So, this is autocovariance of the output in steady state. So, the process is stationary in steady state. So, we can summarize now. For small times the response is non-stationary, the covariance is a function of both T1 and T2 and variance is a function of time. For large times the response becomes stationary, that would mean covariance is a function of time lags and variance becomes time invariant. In the present case mean is always 0. When the covariance becomes function of time lags and variance become constant, we say that the system has reached a stochastic steady state. If damping is 0, the system fails to reach a steady state. This notion of transient state and stochastic steady state is synonymous or is analogous to the notion of periodic steady state and transient states in harmonically driven single degree freedom systems. If you recall, for small times single degree of freedom system under harmonic loads, the response will be aperiodic, and as time becomes large the response becomes harmonic with its amplitude and phase becoming independent of time. So, there is an analogy between stochastic steady state and harmonic steady state. So, I leave this as an exercise. You now consider a single degree of freedom system which is driven by a combination of a harmonic load and a random process, f of t with non-zero initial conditions. So, this p and lambda are deterministic, therefore, p cos lambda t is a mean of the excitation process, but f of t is a 0 mean Gaussian white noise process with this covariance. Now, the question is you need to discuss the nature of steady state response of x of t. So, it has both components of harmonic steady state and a stochastic steady state. So, you have to see if there exists any interaction between them and what exactly happens as damping becomes 0 and the driving frequency goes to the natural frequency of the system. So, what are all these issues? If you discuss, you would appreciate the points being made in the context of excitation under system under stationary excitation. Now, what happens if the excitation is non-stationary? So, if you consider now a single degree freedom system under a Gaussian modulated white noise excitation. By that I mean the excitation is obtained by multiplying a zero mean Gaussian white noise process with a modulating function or an envelope function E of t. This E of t is given here, it is sum of two exponentials and f of t is a stationary white noise. The right hand side here, although it has a stationary component, the process itself is non-stationary. Now, what is x of t? The system starts from rest, therefore, Duhamel integral gives the complete solution. Therefore, this is 0 to t h of t minus tau E of tau into f of tau d tau. What is expected value of x of t? You take expectation on both sides, E of t is deterministic. So, I get expected value of x of t is 0 to t h of t minus tau E of tau, it is deterministic, therefore, it is outside this expectation operator, and we have expected value of f of tau d tau equal to 0, because expected value of f of tau is 0. This is a kind of a notional representation of the excitation process. This black thick line is the E of t and this is the random excitation. This actually strictly speaking does not correspond to f of t being a white noise, because white noise has unbounded variance and we cannot really, it is not physically realizable. So, what is shown in red here can be viewed as a band limited noise where the bandwidth is sufficiently large and therefore, we can notionally represent that. So, in any case the excitation looks like this red curve. Yes, now how does the covariance look like? If you now take expectation of x of t1 into x of t2, there will be expectation of a double integral and I will have E of tau 1 and E of tau 2, f of tau 1 and f of tau 2. Rearrangement of this will lead to the expression for the output autocovariance in terms of input autocovariance ff of tau 1 comma tau 2. This is nothing but I into delta of tau 2 minus tau 1, and again we can carry out one of the integrations by replacing tau 2 by tau 1 and we are left with an integration with respect to only tau 2. This again can be integrated if we know the model for E of tau 1, we can easily evaluate this integral, and if you put t1 equal to t2 we get the expression for variance and this is the expression for variance. Now, we have in the integrand not only h square of t minus tau, but also multiple of E square of tau. H of t again is 1 by m in terms of sine and exponential function we can plot, and we can derive the expression for variance of the output, and I have shown here the plots of variance of the response for different values of eta, and you can easily make out that the response is a non-stationary random process. This is to be expected because input itself is non-stationary. So, naturally the output is very likely to be non-stationary, and that indeed is what is observed through the analysis. We now move on to the description of input output relations in terms of frequency domain description of the system. So, we consider again the system driven by f of t, where f of t is now a stationary random process. As we saw, the notion of power spectral density function is valid only for stationary random process. So, we are restricting input to be stationary and we assume that system starts from rest. So, f of t is a stationary random process with 0 mean and autocovariance CFF of tau and power spectral density SFF of omega. And we restrict our attention only to steady state response of x of t. As we have already seen in the steady state, x of t is a stationary random process. Therefore, I can talk about its autocovariance as well as its power spectral density function. So, the question now I am going to discuss is what happens to the power spectral density of the response. There are different ways of solving this problem. One is to write the develop the model for autocovariance of x of t as function of t1 and t2 and allow the limits of t1 and t2 go to infinity with t2 minus t1 being finite, you will get the autocovariance of the output, and then you can consider the Fourier transform of the autocovariance. Or a simpler alternative would be to consider the definition of power spectral density function, assuming that system is already in steady state. The transients have been dissipated and system is responding in its steady state. So, the power spectral density of x of t is given by this is by definition. Now, xt of omega is the Fourier transform of sample of x of t, where capital T denotes the fact that we are defining an associated function xt of t to be x of t for t and 0 otherwise. So, as we have already done, we will analyze the Fourier transform of this function and then allow this limit t to infinity. So, this is the input output relation for the sample of Fourier transform of f of t and the output x of omega. Using this, I can now construct the expression for power spectral density function of the response, and this is what I get. H of omega is the frequency response function of the system. So, here we have h of omega into h star of omega, which becomes modulus of h of omega whole square, and I have f t of omega into f t star of omega, limit t tending to infinity 1 by t. H of omega is deterministic, therefore, it gets pulled out of the expectation, and what remains inside is nothing but the definition of power spectral density function of f of t. Thus, I have now the output power spectral density function Sxx of omega in terms of the input power spectral density function Sff of omega, and this is obtained by multiplying the input power spectral density function by the square of the amplitude of the frequency response function of the system. So, that is pictorially depicted here. This is the input output relation for power spectral density function of the system. This is output power spectral density, this is input power spectral density, and this is the system function which is relevant for this input output relation. So, it is now h of omega whole square, which serves as the system function or the transfer function. This would mean that if we carefully look at h of omega whole square, it has a peak near the system natural frequency, and if SFF of omega, for instance, if it is a band limited function, the output power spectral density will be product of these two. So, that would mean the system will permit only those frequency components in the input which are near the large values of system transfer function to be manifested in the output power spectral density, or in other words, the system behaves as if it is a filter to pass frequency components in the input selectively through its transfer function. So, to see that, we can consider now a few input output relations. Suppose red line is the power spectral density function of excitation, this is this, and blue line is the amplitude of square of the amplitude of system frequency response function. The product of this will be this, right. So, in the output, most of the power is concentrated in this region, although the input has frequencies at several other frequencies, the output chooses to have higher power near the system natural frequency. In that sense, the linear system is behaving like a filter. So, this is a different choice of relative values of dominant frequency in excitation and dominant frequency in the system transfer function, and the output will now peak at a frequency which is neither the natural frequency of the system nor the dominant frequency of the output. Okay? So, this is off resonance, the input and the system transfer function are off resonance. Now, if the peaks come to close to each other, the input as well as the system transfer function, again there is substantial increase in the energy, and you can see that is almost like a resonance condition in deterministic analysis. So, the output power, the average power in the output process tends to get magnified in those frequency regions where there is higher energy in higher power in the input and the value of the transfer function is high. We have been talking response in terms of only displacement. We could also ask response in terms of velocity or reaction transfer to the support, so on and so forth. So, that would require now description of derivative processes. I have already introduced the notion of mean square derivative for a random process. Now, let us see what is its implication on frequency domain description. You recall now the power spectral density of x of t and autocovariance of x of t are related through this pair of equations. These two functions form a Fourier transform pair. Now, we have already defined the autocovariance of the derivative process can be obtained by differentiating the autocovariance of the parent process twice in this manner. Now, for Rxx of tau I will use the representation in terms of power spectral density function, and if I now implement this differentiation I get Rx dot tau to be 1 by 2 pi minus infinity to plus infinity omega square Sxx of omega into exponential I omega t d omega. Now, if you compare this with the definition of Fourier transform pair, you will see that the Fourier transform of the autocovariance of the derivative process is nothing but the power spectral density would be omega square Sxx omega. This is the power spectral density function of the derivative process. Similarly, you can consider the autocovariance of acceleration process. If x of t is displacement, x double dot will be acceleration. This will be second derivative of the autocovariance of the velocity process. So, using a similar logic you can show that the power spectral density function of the acceleration process is given by omega to the power of 4 Sxx omega. Now, let us return to the problem of single degree freedom system under Gaussian white noise excitation and consider the response analysis in frequency domain. So, we have the system equation here mx double dot plus cx dot plus kx equal to f of t. The system starts from rest, the expected value of f of t is 0, its autocovariance is given by the Dirac delta function as shown. Now, the input output relation will be Sxx of omega into h of omega whole square Sff of omega, where Sff of omega is a constant, right. So, I get I into h of omega whole square. Therefore, and h of omega here is 1 by m omega n square minus omega square plus I 2 eta omega omega n. So, this is the power spectral density function of the output process. If you recall, we have already derived the autocovariance of the response process by using time domain representations, and in steady state I have already shown that the autocovariance function is given by this function. Now, I have now derived the power spectral density function of the response in the steady state. I leave it as an exercise to show that if you take the Fourier transform of this, you indeed get the power spectral density function that we have just now derived, or in other words show that the autocovariance given by this and the power spectral density function given by this form a Fourier transform pair. Similarly, we know that Rxx of 0 is the variance and that is given by I 4 eta omega cube m square. The area under power spectral density function is also related to the variance. So, the variance in steady state can also be obtained by a pure frequency domain analysis, and the exercise is to show that the area under the power spectral density function is indeed the variance, which is this, which has been obtained by a time domain analysis. Now, evaluation of this type of integrals requires the use of Cauchy's residue theorem, and we will return to this in the one of the next lectures, but to prove this, the hint is that you have to use that residue theorem. Now, a general remark at this stage is in order. The study of random vibrations can be viewed from two perspectives. One is motivated by our interest in study of failures of structures under loads such as earthquakes, wind, waves, guideway unevenness, so on and so forth. But there is yet another important application of random vibration principles, and that occur in laboratory work. Actually, one of the basic issues in experimental studies of linear dynamical system is the measurement of frequency response functions. The whole idea of the whole process of measurement of dynamic characteristics of engineering systems, that would mean frequency response functions, and from that the natural frequencies, modal damping, mode shapes, etc., also is based on principles of random vibration. Now, there are certain results in this context that can be derived at this stage based on whatever we have learned so far, and they can be illustrated like this. So, let us start with the input output relation in time and frequency domain. So, if x of t is the input for a system with impulse response h of t, y of t is convolution between x of t and h of t, and similarly if x of omega is the Fourier transform of the input, the Fourier transform of the output is obtained by multiplying the system frequency response function with the input Fourier transform, that is this. And the input output relation for power spectral density function we already defined, but now let us consider the cross power spectral density function between y of t and x of t. This by definition is this, limit 1 by t y t of omega into x t star of omega. Now, I know y of omega is h of omega into x of omega, I will substitute that here and I get s y x of omega as h of omega into s x x of omega. Based on that, I get an estimate formula for the frequency response function, which is s y x of omega divided by s x x of omega. So, if you are doing an experiment, you have to gather time histories of x of t and y of t and use statistical procedures to estimate s y x of omega and s x x of omega. These are fairly standard tools, we will discuss this later, and if you take the ratio of that, you get h1 of omega. Whenever we measure x of t and y of t, there will be measurement noises that will create certain problems. Before I come to that, we can also consider another relation that exists, namely now if you consider power spectral density function of the output, this is the definition, and if for yt of omega, if I write h of omega into xt of omega and examine this relation, I get sy y of omega to be h of omega into sxy of omega. So, I get another definition for the frequency response function, which is sxy of omega divided by syy of omega. Mathematically h1 and h2 are the same, but in an experimental work they will not be the same because of measurement noise and other issues. We also have of course syy of omega as the square of the frequency response function multiplied by sxx of omega. So, if you are interested only in the amplitude of frequency response function, this is yet another formulary for that. You divide the output power spectral density function divided by the input power spectral density, you get this function. We can define now the coherence function between x and y. If you do that, this is actually the definition, square of the coherence. If you substitute all that formula just now that we have derived, you can show that coherence function is 1 between x and y. This is not surprising because system is linear. You can show that this coherence function is ratio of h1 and h2. This is a small exercise. In an experimental work, if you were to measure the coherence and plot it, you will see that it will not be uniformly equal to 1. because of presence of measurement noise or because of structural nonlinearities, so on and so forth. So, the plot of coherence function and its departure from unity is taken as a quality of measurement of frequency response. If it is deviates too much from 1 at certain frequencies, at those frequencies the transfer function is not measured acceptably. So, we can summarize the importance of coherence in FRF measurements. If we consider this question, we should notice that measurement of FRFs is adversely affected by several factors such as structural nonlinearities, electronic noise, and there are several signal processing issues. Later in the course we may have a chance to discuss this. So, because of this the coherence will never be equal to unity, I mean not always be equal to unity. So, therefore, coherence serves as a valuable tool in assessing the quality of measurements. Greater the departure from unity, poorer is the quality of measurements. Now, an application of dynamics of single degree freedom system under white noise excitations. This application arises in the context of modeling earthquake ground motion. Imagine that this is the bedrock and overlying this there is a soil layer, and when an earthquake occurs, whatever displacement that occurs at the bedrock level propagates through the soil layer and appears as the ground shaking. We are basically interested in the way the ground shakes because buildings are housed on this. Before the construction of any structure, if you study the ground motion, we call it as free field ground motion. In the sense there is no engineering structure yet constructed on that structure. So, most of the course of practices define this free field motion in some manner. Conceptually, to make a model for free field ground motion, one of the model is proposed by Kanai Tajimi. In this model, it is assumed that at the bedrock level the ground acceleration is a white noise, and the soil layer is modeled as a single degree freedom system where mg is the mass of the soil layer, kg is its stiffness, and cg is the damping. And this is the free field point and this is the bedrock point. The free field motion thus gets characterized in terms of the power spectral density of the base motion multiplied by this transfer function associated with the soil layer. So, how does it take place? If you write the equations now, this is the equation for the total displacement of the ground, that is the total displacement of the mass. So, this is mg u double dot, Cg is a damping force which is function of u dot minus xb dot. Similarly, Kg is the spring force which is function of u minus xb. So, if you now write from this the expression for absolute acceleration at the ground level, we get this expression where Cg by mg is written as 2 eta g omega g and Kg by omega g is written, Kg by mg is written as omega g square. So, this is the expression for the total acceleration at the ground level. Now, you can as well define a relative displacement u minus xb, and the relative displacement is governed by this equation where in the right hand side I get the acceleration level at the bedrock, whereas here on the right hand side you will get damping into the velocity plus stiffness into the displacement at the bedrock level. Now, we can do a frequency domain analysis of this absolute acceleration, and if we do that we get the Fourier transform of the absolute ground acceleration can be written in this form, and based on this Vt of omega is now obtained as through the input output relation of this equation. If you substitute that here, and use the definition of power spectral density functions in terms of this expectation, I get the power spectral density of the ground acceleration to be in this form. This is the well known Kanai Tajimi power spectral density function. Its derivation is based on how a single degree of freedom system responds to support motions where support accelerations are modeled as white noise processes. Omega g is the natural frequency of the ground, eta g is the damping in the soil layer, I is the intensity of shaking at the bedrock level. Typically the power spectral density function appears in this form, it is unimodal, and this peak occurs at the natural frequency of soil layer, and this bandwidth depends upon eta g, the damping in the soil layer. So, this power spectral density function essentially captures the possibility of ground resonance, because the system is modeled as a single degree freedom system. There is one possibility to allow for one resonance, and this is very easy to use in random aberration analysis, because in frequency domain analysis the power spectral density functions are obtained by simple multiplication of transfer function square into the input power spectral density function. So, it is very easy to use. The problem of course here are that this model does not recognize that the ground acceleration is actually a non-stationary random process, and of course the soil itself is taken as a single degree freedom system, whereas soil layer is a continuum, it can have probably more than one natural frequencies in the frequency range of interest. This can be remedied, this can also be remedied. How to introduce non-stationarity into ground acceleration? We can multiply the stationary random process whose power spectral density is the Kanai Tajimi power spectral density by a deterministic envelope function. This deterministic envelope function captures the non-stationary trend that is observed in earthquake ground motions. So, an example could be S of t could have a Kanai Tajimi power spectral density, and these envelopes for example could be sums of this we have seen just a while before, and a similar curve like this in the sense they essentially capture this type of behavior in time. The envelope functions either they can be expressed as differences between two exponential, or even if you take e raised to minus t, it also has qualitatively this type of behavior. So, both these types of models have been proposed in the literature to capture transient behavior. So, this is how conceptually it looks like. This is sample of S of t, and upon multiplication by E of t I get the transient realization of a non-stationary random process. This red line that is shown here is the envelope. So, with this models that we have developed, we are able to now proceed a bit further and we are able to develop simple models for earthquake ground motions. Now, how does the system itself respond to Kanai Tajimi ground motions? So, this is my structure, that means I have bedrock, this is ground, and on this I have my structure. The way we model it is, this itself is modeled as, this is soil, the output of this is say u of t. A simple version of modeling would be to, this is my structure, so call it as M, K, C, and this u of t appears as support motion for this structure. That means there is a kind of a cascading assumption. We could as well make a 2 degree freedom system . This is soil, this is structure. In this model we are allowing for possible interaction between structure and the soil, whereas here we are ignoring that. If we consider this simple situation first, it is quite straightforward to deduce the output power spectral density function by simply multiplying the transfer function of the soil with the transfer function of the structure and the power spectral density at this bedrock level. So, this is so called cascading assumption which can easily be implemented in this particular case. With this we will conclude this lecture.